The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So how many of you have exposure or have taken any heat transfer classes here? Okay, it's about half of you. Cool. So can you start by telling me what heat is? It sounds like pretty basic. Yeah, okay. It's a form of energy. What are the units of that? Cool. And what about heat transfer? What are... I guess that's pretty self-explanatory, just transferring heat. What are the units of heat transfer? Generally, you're trying to figure out how much energy is being transferred per second. So you're going to have a joule per second, or watts, yeah. So what are three major modes of heat transfer as well, if you remember? Right, awesome. And for people who haven't seen this material before, tell me if I'm going through it too quickly when I start talking about it. But can people explain what the difference is between the three types of heat transfer? What?
Instead of giving someone else a shot.
Yes.
Conduction is just through direct contact.
Okay.
Convection is basically conduction except through a fluid that's moving.
Cool. In radiation? Yeah. I think this is more generally just heating through electromagnetic waves. But yeah, so that's kind of the three sort of big modes of heat transfer. We'll be talking about convection and conduction a lot more later when we're doing, say, cooking in stoves, because that plays into that a lot more, like when you're putting a pot on a fire, but when we're dealing with solar stuff, we're going to be dealing mostly with radiation. But while we're on the topic of heat transfer, I might as well give you the equations for the other two, but we'll start by talking about radiation. So when we're dealing with radiation, when we're dealing with radiation, we're thinking of objects giving off energy in electromagnetic waves. The only thing that it really matters when you're dealing with this is what the temperature of the object is. So you can approximate things as, or there's an equation for it, which is the heat transfer from due to radiation is the Stefan-Boltzmann constant times the area of the surface area of the object times the temperature to the fourth, which is an important equation to know. For convective heat transfer, you have a different equation, but again, like this isn't that relevant, so I'm going to move on to talking to you guys about different types of solar technologies now. So the first one we're going to talk about is Sodus. Do you have any? Okay, so you have Sodus, you have solar thermal. So solar thermal is when there are different types of technologies. It's where you're using heat from the sunlight directly. So you're using solar radiation to heat things, and there are three different sorts of big ways you can do this. You can use it for cooking and drying, you can use it for heating of water, and you can use it for generating electricity. And you also have photovoltaics, which we worked with last time for generating electricity. So Sodus, the way Sodus works is you fill bottles with water and you close the cap, then you leave these bottles out on a rooftop and you expose them to sunlight for about 6 hours, and you can store, like, in the UV light from the sun plus the heat from the sun also kills the pathogens and bacteria inside the water. If you remember, do you guys remember from last week when we were playing with the bags? There was a Sodus bag. Does that sound familiar at all with the plastic sealer? Yeah. Why are you laughing?
Because I spent like 2 hours trying to make one.
Yeah. So Sodus is a really cool technology. It's an example of how you can use solar energy to purify water. There are other ways you can use solar energy to purify water too, but this is supposed to be one of the better ones. So I guess we kind of jumped ahead by showing you a really good Sodus technology last week before talking to you about Sodus as like a technology. But in most of the developing world, the companies that are promoting Sodus, what they do is they tell people to use 2-liter bottles, which are available in a lot of the developing world, and fill them with water and leave them out on your rooftops. Can you guys think of any ideas or any reasons why this is not a good idea? Or what isn't the best, why this isn't the best solution to using this technology or best implementation of this technology? And why, say, a bag would be better? So what are some of the problems with a plastic bottle? So you have this plastic bottle, it looks kind of like that. Yeah.
We don't have the perfect useful picture has, then the bottle might fall over, fall off, not sit. Whereas the bag, at least last week's bag was like more just floppy.
Yeah. I actually haven't seen that particular issue before, but that's a good point. What about in terms of transportation? How easy is it to get a plastic bottle that's shaped like this? What if I wanted to provide an entire community with these, how would I send it to them? I would have to ship a giant container with 2-liter bottles, and they don't really pack well at all, right? You need to fill like a crate of 2-liter bottles, and it just seems really silly to ship an empty container or a container of empty water bottles. In places where they have 2-liter bottles, it's a really good technology because, I mean, if they're just taking existing things that they already have and they're using them, repurposing them for this, then it's great. But otherwise, it doesn't seem to make that much sense to try to fly them in. And that's what some of the companies that were really promoting Sodus heavily in the beginning were doing. They were trying to ship 2-liter bottles in bulk to communities to get them to use them. Can you guys think of any other disadvantages to using these water bottles? What about, so how does okay, maybe I'll go a little bit more into how the technology works. So you have your water bottle like this, I guess. That's not how it looks. With your capped water bottle, it's filled with water, like, say this is all water. So what happens is you have sunlight coming from here, it's heating up the water. Yes.
Also, surface area of the receives sunlight into this diameter rather than a flat plastic bag or any other container. So I guess the water on the bottom half of the bottle won't get as much. It will take longer to purify.
Yeah. Because water and your plastic both absorb some of the sunlight, you have a lot of it being absorbed by this fluid. And what they say is if you have, if this depth is more than 4 inches, that Sodus's effectiveness is dropped by maybe 50%, I think is what they say. So, yeah, so that's another problem. I think a 2-liter bottle is about the right size, so it's still in the range of the right size. So you're not going to have you're not going to have more than 4 inches there. But that's definitely something to take into consideration. What about place? So what about the cap? Can you guys think of why the cap might be a problem?
It's not transparent. It doesn't have any water. There's in the threads where you bottom it, probably won't get purified, and then as you're pouring water out, it makes it.
Yeah, that's exactly one of the biggest problems with Sodus with using a water bottle is just because the region in this area where the cap is just doesn't, I mean, it's opaque plastic, so your UV rays most of them are getting blocked by the plastic, and so your bacteria don't die necessarily over there. So that's why the bag that Sean Frayne came up with, the Sodus bag that you guys saw the other time that used 2 one-way valves, works a lot better because the entire thing is transparent. And there was a lot of work that people were trying to do, trying to redesign this into a better system. So they looked at the problems with transportation with the 2-liter bottle, and then they came up with another bag that was kind of just a bag that had a handle here, and then it had the same sort of twist-on cap over here that a 2-liter bottle does, like that. And then they made the back of the bag black so that it would heat up more, which was a pretty cool design. But then we still had problems with, for one, having expensive molded parts is also really expensive because you can't really fabricate that everywhere. Like you can't go into a village and try to create something that looks like this, or even something that looks like this. Whereas if you have a simple plastic sealer, you could make one of the Sodus bags that we were working on, or that we saw last week. Has anyone not seen these Sodus bags from last week, or have no idea what I'm talking about? Okay. And how many of you have heard of Sodus before? Okay. So this design sort of went from this iteration to this iteration, and then Sean Frayne came along and worked on it a little bit and came up with the next iteration or came up with his technology, which is just like really, really good technology. In terms of usage, because I want you guys to start thinking about these technologies and how you would use them too, what's another problem that is with this? You're supposed to take this, you're supposed to leave it out in the sun for 6 hours, and then or 6 hours to 2 days, depending on the weather conditions, and then it's supposed to clean your water and you're supposed to drink it. Yeah.
I have a question on how it works. Like, what is it, like a chemical inside that mixes with the water to purify it?
No, you just take water, right? And you leave it out in the sun, and the UV rays from the sun kill the bacteria. It breaks down the bacteria.
So any container would be good?
Any container, as long as it's clear and UV transparent, or transmissive.
What does Sodus stand for?
Solar disinfection. I should have explained that. Yeah, sorry, I guess Sodus stands for solar disinfection. So you're purifying water just using sunlight.
But is it like a company that's on the market?
It's a technique.
Oh, okay. Oh. That's what I was confused about. So then, like I know that BPA-free water bottles are in the news, right? Because of all the toxins that plastic produces when it's an extreme heat or like an extreme low or extreme high temperature. Is that a consideration? The idea is that like any like recipient of water can be used for it, but is that
So generally, leaching from plastic is it's a problem that's on a much smaller scale than having unsafe drinking water. And so if you had to choose the trade-off between having some plastic potentially leach into your water and drink it, and over like dozens of years that might cause some health problems, versus having unsafe drinking water, like you would definitely choose the unsafe, or you would definitely choose the using Sodus to drink your water. But yeah, that is that is one of the bigger concerns with Sodus. Cool. Are there any other questions about Sodus? All right. Then I'm going to go into solar drying. So solar drying is another technology that is used in a lot of places in the world. And the idea is basically that you take fruits or whatever, and you dry them so that you can preserve them. And the thing is, like in a lot of places, you'll have farmers who are growing something, and they'll all have crops that grow at the same time. And so they'll harvest, and then they'll go take them to the market. And because there's an overabundance of these fruits or something, people aren't getting their peak, like they're not getting as much as the money as they can for these, for their fruits, because there's way too much of, like there's way more supply than there's a demand for it. And if they don't have a very good way of preserving food otherwise, so they can't like refrigerate these fruits. So if they don't keep them refrigerated, then they're just going to spoil. So it's either sell at a low cost or don't get anything for them. And so their food preservation is a pretty big deal as well. And so you can use solar energy to also dry fruits. And this is a project called Fruits of the Nile that works in Uganda, where they do that. And then I'm going to go to talking about solar thermal panels for water heating. I don't know if you guys have seen these. These are taken from the US, these pictures. But have any do any of you have exposure to solar thermal? Okay. So you're basically what you're basically doing here is you have well there are two types of systems which I guess are on the next slide, but so you have two different types of systems, but this is a little bit more complicated than it needs to be. So basically the idea is you're taking in sunlight, and using the sunlight you're heating water or some sort of fluid. And so you have sort of this container that's shaped like this, or you have tubes that have water or some container or something running through it. Sunlight hits this container, heats up the water inside these tubes, and then you get, and then you store the hot water in a tank. So that's a direct solar thermal system. There's also indirect solar thermal systems where instead of having your water being heated directly, you have a heat exchanger here, and then you have some sort of fluid that goes through the system, and then you have your reservoir or something, and what's heating the water is this like hot fluid, like the heat exchanger is what's heating the water. A heat exchanger is just something that transfers heat from one thing to another, if you were wondering. And so there's a lot of, solar thermal is way less efficient than solar PV, photovoltaics, but it's also significantly cheaper. I don't have numbers for you for that, but you don't want to think of solar thermal as only being a small scale technology, because there are large scale applications of it as well. This is sort of like the smallest case you can think of. It would be like having one of these for your household your household to heat water for showering or something like that. And then you have larger scale versions of this too, which is the Luce project in the Mojave Desert, and it's the largest solar thermal electric installation in the world. It has 350 megawatt peak output, and if you can see like this picture, those are 3 people standing next to it. So this thing is massive. It's on the order of kilometers. Yeah, and the way this works is it's similar to this, except you have your pipes that have water in them, but then you have these concentrating troughs that are focusing all of the sunlight onto the pipes. And so you get the way this normally works is you have this technology works is you heat up water to the point where it turns into steam, and then you have the steam powered turbine, and then you produce electricity using that. Yeah. They what?
They use oil in the pipes.
Oh, they use oil?
Yeah, they use oil in the pipes to heat it up and bring it to the generator. Cool.
Did you do research?
Yeah, I did energy, solar energy consulting this past summer at DOE. So like we looked at the new energy solar CSP power plants in the US.
Cool.
What does it say thermal electric? Like the thermal part, I guess, but what about the electric?
Those power plants are used for they're used for energy generation.
So
they use,
Okay.
so these generate electricity. Yeah. Does that make sense? So you have steam, which powers a turbine, and that turbine generates electricity. And so you not only do you have, you're not doing something simple like heating water anymore. You're also using the same technology, but now you're generating electricity from it. And I thought I would throw this in just for fun. This was another cool, this is a project that I was working on last year in Brazil. And it's a really low cost solar water heater. But the reason I threw this in was because a way a lot of these lower cost, cheaper ones work is they work based off of a thermosiphon. And so basically what happens is when you have, what happens is in a system like this, you'll have a system like this that's connected to a tank. And so water heats up in this, and as water heats up, you like, if you remember from, I guess you learned this in middle school, hot air rises, like things like that. So hot water also rises. So you get a flow of water towards the top of this thing. So what happens is if you connect this to a reservoir, you'll get, and you basically get a flow caused just by the temperature differential in the water. So hot water will flow into this reservoir, and it'll get displaced by cold water. And so you're regulating the temperature and heating all of the water consistently, which is pretty cool because with a system that's based off of a thermosiphon, you don't need to throw in a pump or something like that to extract the water from your, yes.
What system is this? Just a heat siphon?
Yeah, it's just a heat siphon. But yeah, so it's just a passive way of doing the same sort of flow. Now I'm going to go into, are there any questions on any of what I've talked about? I know I did a really, really cursory job of heat transfer earlier, but that's because we're going to go more into it when we're talking about photovoltaics. And more next week when we're going into conductance and convection for cooking. But are there any other questions that you guys have about what we just talked about? Okay. So we're going to move on to photovoltaics. I'm going to try to explain to you how solar cells work. I got a lot of this information was taken from this website called PV Education. It's actually it used to be called PV CD-ROM, which I thought was pretty funny because it's a website now. So I guess it's been around for a while. How many of you are you familiar with this? Yeah, okay. It's a great resource for a lot of information that you might, and it'll answer a lot of the questions you have, and it does a pretty good job of keeping its level like basic enough for you to understand, plus being mathy enough for you to actually understand what's going on too, if you're interested in that. So let's start by, so yeah, you should go on that and read up on more of it if you have time and you are inclined to learn more about how photovoltaics work. But anyway, the temperature of the sun, does anyone know what the temperature of the sun is about?
Is it 10,000 Kelvin or something?
That's a little high.
It's like a million Kelvin.
That's a little higher. It's less than that. It's about 6,000 Kelvin.
60?
6,000. Well, so to be fair, when you have you have the sun and it's kind of like that. You have the core where there's fusion going on, and I think the core temperature is maybe like 20 million Kelvin or something like that. So something like that. It's something ridiculously high. I might be off by an order or two of magnitude in some direction, but it's not really that important. But what happens is most of that energy is blocked off by the sort of dense hydrogen around here, and then you have the very end of you have the outer rim of the sun, which is at about 6,000 Kelvin, which is what's radiating most of the heat to the Earth. And so that's where we get all of our energy from. It's kind of cool to look at a graph of what the energy, of what the irradiance looks like. So this is what wavelengths. So this is a weird graph. The red, green, and blue are 3 different types of lighting, and the purple is what the sun is. So you can ignore the other 3, but you should look at the purple to see what wavelengths of light the sun outputs at. It's interesting because you can see that this is also on a log scale. So you can see that the bulk of the light is in the visible spectrum, which is cool because, yeah. But to measure how much energy is being outputted by the sun, you can just integrate under this curve to find out, to measure the entire thing. Do you guys know what the energy from a single photon is based off of the wavelength? Do you remember the equations for that? So you can calculate, someone say? Yeah. It's Planck's constant times c over lambda. So you have this. You don't need to know this equation, but it'll give you a good sense of how you can derive how much energy is coming from a photon or a wave. So this is Planck's constant. This is the speed of light, and this is the wavelength. And so what's important from this is that the lower the wavelength, the more energy you have. So yeah, your blue light is going to have more energy than your red light. Does that make sense? Cool. So you have this. So you have your sun. It's outputting. So you have the sun. What you're looking at is radiating a bunch of electromagnetic waves in the form of, I guess, photons to the Earth, which is here. And then we're trying to look at what happens. Like if we're trying to follow the path of this radiation, we can see that not all of it reaches the Earth, or not all of it that reaches the Earth makes it to the surface of the Earth, because a lot of it is absorbed by our atmosphere. And so this is a kind of graphic that'll show you where a lot of energy is lost. So only about 70% of it is actually directed to the Earth. 3% is scattered to space, and 18% is absorbed by the atmosphere. Now we're going to go into how a solar cell works. So, yeah, okay. So this is like also a little bit complicated. So you have a solar cell, which looks like this. If you haven't seen one before, they're super fragile. We can pass them around. These are broken ones. Evergreen Solar was kind enough to donate 200 of these to us for this lab and for our projects. So we'll be playing with them and wiring them up today. So are you? What happened?
I wanted to put my thumbprint on it, and I put.
Yeah, they're super fragile. You can see why. Like, it's one of the reasons why working with solar cells is such a pain, because they're so easy to break. Like when you try to, and you have to solder them together to make them work. So it's kind of difficult. But we'll get into that later. So how do they work? So you basically have 2 layers in your solar cell. As is described in this drawing. And what happens is you have a photon coming in. And for one, they're semiconductor. So you can tell me what a semiconductor is. Okay. Yes.
It's what is it like? You have a valence band, you have a conductance band, and you have to have exactly the right band gap in between the two, so that when a photon hits it, when a photon is incident on it, it like activates exactly what you need it to.
That's correct. Yeah, that's. Did everyone understand that? Okay, so basically what happens is you have, in a semiconductor, you have things in a pretty like ordered pattern. So you'll have like atom, something like that. And so they're all bound in this lattice. And so what happens is they don't have free electrons right now, but you can get a free electron from them if you excite the electron with enough energy. And so if you have a photon coming in and it has the right amount of energy to excite an electron out of one of these bonds, then the electron, or the valence electron, or out of the lattice, the electron becomes excited, and you then get an electron hole pair. And this is all a gross simplification of how this works, because a lot of this is like, I mean, you can't really just think of, you can think of electrons as particles that are moving across a circuit, but that's not actually how it works. But for this, you're gonna like assume this simplification makes sense to try to like conceptually understand how it works. And so what happens is you have like a photon hitting this, so you get this electron hole pair. And you can think of a hole as where the electron was before. And so now there's this space where this electron was, and so it's kind of positive area because there's less electron, like there's no electron there anymore. So you can think of it kind of like a bubble in a fluid almost. And so this electron wants to go back into this bubble. And this bubble is free to move as well, just like the electron is free to move through the structure now, because it can go through it. And so what happens is but the thing is that you're using two different types of silicon, and one of them is an N type and one of them is a P type, and the N and P just stand for negative and positive. And so the other thing is you can dope silicon, and what that means is you put impurities in it, and that creates a permanent electric field inside the silicon. And so one of your sides is more positive and one of them is more negative. So when you create this electron hole pair here, they're going to want to be pulled towards opposite directions, just based off of drift. And so once they get pulled to either side, if you create a circuit and you put a load on this thing, then you can have the electron flow through here and go back, and if the hole is here, then it'll close the circuit again and combine with the so that's a very like simplified way of how photovoltaics work. Does that make sense to people? Are there any questions about that?
So the positive terminal becomes the N type, the N type of band. The positive terminal is the negative terminal.
No, the N type should be the negative.
Huh?
The N type is negative.
There's a really good animation in PV education that shows the two different sides of the electron.
It's true. We could actually just watch it. I had it open. Okay. Yeah. Anyway. So we can. So that's basically how photovoltaics work. You get yes.
Doesn't sunlight hit the junction though? Isn't that how? I mean, because you have like the holes and then the electrons on the side, creating the the opposite electric field. Doesn't the light hit the middle? I mean, that was my understanding. I could be wrong, but I thought it hit the middle.
I'm not sure. That's not how I understood. I don't think. I feel like. So the reason. So the absorption coefficient of silicon is really low. So you have a lot of different solar cells, right? You have amorphous silicon. You have like multi-crystalline silicon and stuff. And the reason why you have like thin film cells as well. But the reason why silicon cells are so thick is because the absorption coefficient is so low that you basically need a thicker area to be able to absorb most of the light. I'm not answering your question, am I? You think that?
So my understanding was that it would hit the middle, like not exactly the middle, but you know how like in the middle you have the opposite electric field because of the holes and then the electrons on the sides.
Right.
So like if this is your N and your P, then you'd have holes here and you have electrons here for the opposite field. And my understanding was that it would hit the middle and the field would force the electrons to go in one direction, which would then be used to then be helped by an external circuit.
Well, there are a few like factors in play. So you have one side that has. Here, I can show you a video on how. Okay, I don't know if this will work. So this is from this PV CD-ROM website, and so it's an animation saying how things work. And so if you have a moderate field, you have two things that work. You have diffusion, and the thing is, in diffusion, the way diffusion works is if you have a lot of, if you have a lot of holes on one side and electrons on the other, the electrons want to tend to go to the side where there aren't electrons, and the holes want to tend to go to the side where there aren't holes. And so you have that, but that's working against the positive and negative factor of or the positive and negative charges of the two sides as well. So you have those two kind of balancing each other out in some way. So I'm really confused by this. So once you have, hold on. Okay, yeah. So once you're connecting this to a load, you're now enabling the holes and electrons to travel across this conductive region too, and so they're not only they're not just diffusing and drifting through here, they're also like traveling through. That's still not answering your question?
I mean, so basically I understand the concept. I was just curious whether like in the diagram, you know how there's in the middle region, the depletion layer. My understanding was that's where the electrons were, that's where the light hit, and that's where the electrons were ejected, and then they would move around. But this diagram doesn't seem to be doing that.
Yeah, I'm pretty sure that like the light excites or creates electron hole pairs anywhere inside the entire cell. but I can double check with you and follow up on that as well. Cool, so now we're going to go into some practical considerations for developing world work in solar. Yes.
So, solar panels can't function past like a certain 15 years, right, or something like that. And what exactly is breaking down in this to cause that to happen?
Not really sure.
They often function a lot more than 15 years. It starts to degrade. I think most of it has to do with like actually not the cells themselves, but the glass and all the other materials breaking down, getting scratches and dirty, and just I think a lot of the panels are actually like outlasting their warranties. They have like 25-year, 80%. 25 years, they should still be making 80%. A lot of them are like, I think some of the earlier ones are coming to that time that they're still going pretty well past that. So it's not actually.
So there's nothing we can.
There might be a little bit, but that's not really the biggest. It's mostly, yeah, like the glasses are getting dirty and scratched.
I can also look that up and get back to you on that. Yeah. So let's look at some of the financial tools that are available in order to finance solar. So you can do the four sort of big ones are microfinance, a fee for service, income generation, or smaller systems. And then, so you have, for microfinance, you have smaller payments over a longer period of time. For fee for service, you have a company that owns a PV system and a household that pays the electric bill for it. For income generation, which we saw, I think, in the lighting lecture last week, we saw how people were using solar panels to generate income. You use a system to improve your income stream. So you can, with something like this, you'll have one person with a lot of solar panels who will charge a lot of batteries and rent them out as electricity. And then for smaller systems, you can scale the technology down. So you're not using giant solar panels anymore, but you're using smaller sort of panels to power a lantern or something like that, for example. Yeah, and so that was the bulk of what I wanted to talk about today about solar cells. I guess one of the interesting things, though, to note about them is that it's weird because they're a technology that's very much. There's a quote from Harish Hande, who is the founder of Celco, that's solar is expensive for the rich and affordable for the poor. It's the rich who need subsidies. And it's sort of this weird thing because electricity, for the amount that people need in the developing world, for the amount of energy that they need there, solar is a very cheap solution for that. Whereas the amount of electricity that we're using, like at the scales we're looking at, solar is a very expensive option compared to other sorts of electricity. So it's pretty important. Like, it's pretty important to think about, or it's like important to think of solar as not an expensive technology per se, because I think in the U.S. at least we have that bias as solar being expensive. And Celco makes profit because they sell all of their solar panels without subsidies at all. So I thought that was pretty cool.